Hello everyone. I know you love squeezing things and I do too. So today I'm gonna prove the squeeze theorem. So what the fuck is the squeeze theorem? Okay, so imagine this. You have some kind of graph here and you want to ask yourself, oh, what is the limit of this function when x tends to say infinity, positive infinity? And say it looks fucking weird, it looks something like this, but it kind of dampens out after a while. And then say that you can find two other functions, saying they maybe look like this and this. And you know that this function here, is less than that one, and you know that it's greater than this one. And say that it's completely bounded in between these two, and these two functions, the ones we invented, tend to the same number. Then of course this one here in between gets squeezed between the two onto the same limit. So that is what we're gonna prove today. So actually it doesn't have to look this nice, meaning that this is greater than that, which is greater than that. It doesn't have to hold for all x's, which it looks like it does here. It only has to hold in a small neighborhood of this point. So we say that if x belongs to our neighborhood P, then this thing here implies that, okay, so now we name the functions. The function we actually want to know the limit of, we call f of x. So this is x, y. And say the greater function, we call that g, and the lesser function we call h. Yes, so then that would mean that in our neighborhood which we call P, we know that h of x is less than or equal to f of x, which is less than or equal to g of x. Yes. Okay, so what is our neighborhood? Our neighborhood, P, it is the open interval of our midpoint, which is the value that x actually tends to, because it doesn't have to be in this case where it tends to infinity, it can tend to any finite number. So therefore we have the middle point, we call that a, which is just a number that x tends to, and then we want to subtract some positive interval. So we have like, okay, imagine if we were to look at this, then we want minus something and we want plus something to create this kind of interval here. So, and I will call that a delta p. So therefore the right one is a plus delta p. And now, what more did we know? We knew that the limit of these two were the same. Well, the limit of what? The limit as x tends to a of h of x. We knew that that was equal to the limit as x tends to a for g of x also. And let's call this finite number L. So therefore we also have to suppose that, or no, it is kind of in the description that, okay, if both h and g of x tend to a number, the limit exists and tends to a number that we call L, then we know that this holds. So now let's write down what the fuck does this mean? Well, according to the definition of a limit, we know that for any given epsilon greater than 0, we know that there exists a delta, and I will call this delta age, such that x minus a is less than delta age, implies that h of x minus L is less than epsilon. So if you're not familiar with this definition right here, this essentially just means that if I were to challenge you with any epsilon, and to challenge I meant that I want you to find the interval wherein it is epsilon close to the limit at hand. So meaning that if it were to say we have some kind of function here, looks like that, and we want to find the limit of this specific point, then if I said that, oh, it has to be this far apart, then you can always find an interval right here, so that it implies, sorry, I drew it incorrectly, then you can always find an interval here so that it is close enough. And if you can mathematically find an answer for any given epsilon, meaning that your answer is just a function of whatever I challenged you with, then we know that the limit exists, basically. So that is what the limit means for the function h of x, and let's do the exact same thing for the function g of x. So we also know that for every epsilon greater than 0, there exists a delta g, let's call it this time, such that, and then kind of the exact same thing. So the interval, the distance from x to a is less than delta g, implies that the function value is epsilon away from L. And we also know that from this thing here. So we know that there exists an epsilon p, I called it, right? Such that when x is delta p, sorry, did I say epsilon? Sorry. When x is delta p away from a, that then implies that the statement that we had here above, so h of x is less or equal to f of x, which is less than or equal to g of x. Now, it is really fortunate that this is a YouTube video, so you can scroll back. So now I have to erase like basically everything. So give me 1 second. Now we just combine everything we just mentioned. So we can then denote that for every epsilon greater than 0, we know that there exists a delta p, a delta h, and a delta g, such that, okay, so we have, gonna write down here, I think, yes, x minus a, the distance from x to a is less than delta p, and the distance from x to a is also less than delta h, and the distance from x to a, and just the exact same thing with delta g instead. This thing here implies that. Okay, so what did we have before? Okay, we knew that we had for both g and h, we knew that for every epsilon there existed a delta, such that when the distance from x to a was less than the specific delta, then the difference between the function value and our limit L was less than epsilon. So therefore, when you have anything in absolute values is less than a positive integer, then you obviously know that this thing inside is greater than the negative of that, and it's less than the positive. So therefore, we can denote that minus epsilon is less than, okay, so we had that h was the smallest one, right? And g was the largest, I think it was, yes. So h of x minus L. And so this really should make sense so far, because that's what the definition when this thing here implies that, right? Because the actual thing was the absolute value of this is less than epsilon, but then of course if it is less than the absolute value is less than epsilon, then the thing inside is greater than the negative epsilon. And since from the h of x is less than f of x, which is less than g of x, we can therefore denote that this thing is less than or equal to f of x minus L, which is less than or equal to g of x minus L. From the definition for the limit of g of x, then we knew that this thing here implied that the absolute value of this was less than epsilon, so we just can denote that this is then, of course, less than epsilon. And what does this imply? This implies, of course, that minus epsilon is less than f of x minus L, which is then less than epsilon, which is completely equivalent to the absolute value of f of x minus L is less than epsilon. And this is what we wanted to get to. We have some more work to do. So for the definition of the limit for f of x to hold, then we both have, well, this is the endpoint. You know, when x minus a is less than something, that implies that the function value minus L is less than epsilon. But we have to go back and do some work here. Okay, so what does this mean? This looks like hell, but it really isn't. So okay, we have the difference from x to a is less than something, and it is less than something else, and it's less than something else. So if you imagine this, right? Okay, we have the number line here, and we have a. So maybe the first one says that, okay, so this is x, of course. So maybe the first one says that, oh, the distance between x and a has to be less than 1, maybe. Then this, of course, is, if this is 1, then this is our first interval. And say that the second one says that it has to be less than 1.5, maybe. So then we have another interval. And then the third one says that it has to be less than 0.5. So therefore it has this interval. And then now we look at what does this say. Okay, it says that, okay, this has to be true, so it has to be in between here. And this has to be true, so it also has to be in here. Meaning that, okay, so from just this statement alone, if we ignore this part here, just look at this, then of course it has to be inside the smaller interval, right? Because if it's in the region where it's in one of the intervals but not the other, then the and doesn't hold, right? And then of course the same thing applies when we add the third one, then we just get the smallest interval. So we know that this thing is completely equivalent to saying that x minus a is less than the minimum of delta p, delta g, and delta h. So there, if we now ignore the middle part, what does it say? it says that x is less than the minimum of these three things, always implies that f of x minus L is less than epsilon. So now, if we just denote this as our epsilon, then the proof always holds. We have arrived at the definition statement of what a limit is. And since, so epsilon is always given, but then we can choose our delta from these three things here, depending on the definition for the other two functions, basically. So this is a conclusive proof, since we have arrived at the definition statement of the limit, as I said before. So yes, that was basically everything for me. So before the video ends, I just wanted to quick plug some things. I do coaching calls if you want to study or have any general math questions. I cost like nothing an hour. I'm just trying to gain some experience and help some people, and well, yeah, basically. So yeah, that was everything for me. Hope you enjoyed the video. Hope you understood the proof. If you did not, please leave a comment in the leave a comment exactly, and I will see you some other time. Bye bye.